present my paper, which is recently accepted by monthly notices of Royal Astronomy Society. And my research topic is Extinction-free Census of AGNs in the AKARI IRC North Ecliptic Pole Field from 23-band infrared photometry from space telescopes. So in my presentation, this includes 4 parts, which are introduction, data and analysis, results and discussion, and conclusion. So first, I want to introduce what AGN is. AGN is the abbreviation of Active Galactic Nucleus, and it is a compact region at the center of galaxy, which is ultraluminous. Searching for AGN is very important because AGN could be important contributors to cosmic infrared backgrounds. There are actually several ways to find AGNs, such as based on optical, UV, and soft X-ray observations. However, AGN may be obscured by gas and dust, and those obscured AGNs may be missed by these observations. To avoid missing the obscured AGNs in the universe, mid-infrared survey is very important because it's dust extinction free. So, and AGNs, they have this, AGN, they have strong warm dust continuum emission due to their black body radiation. They also have silicate absorption at 9.7 micrometers, so you can see these features. However, if we want to use mid-infrared to select AGNs, we also need to know there's another kind of source that have a unique feature in the mid-infrared, which is star-forming galaxies. Star-forming galaxies, they have strong path features in the mid-infrared. So it's very important for us to do the AGN star-forming galaxy classification if we want to use mid-infrared. Actually, many works have been conducted to search, identify, and characterize AGNs by using the data from Spitzer Infrared Telescope and WISE Telescope. So this is Spitzer's filter, and this is WISE's filter. But we can see there are actually gaps between these filters. So if the feature of a source falls in the gap of the filter in WISE or Spitzer, we are never able to distinguish whether they are AGNs or not. Therefore, a telescope with continuous infrared wavelengths is needed. Fortunately, we have AKARI. AKARI is an infrared space telescope launched by ISA Struxa in 2006. And it has a unique 9 continuous band in the mid-infrared, which enables us to distinguish AGN and star-formation galaxies more effectively. So these are the data we use in this work. We take the data from the AKARI NEP Wide Field Survey. So this North Ecliptic Pole survey was one of the large area survey of AKARI, which contains 5.4 square degree. So this is the coverage of the AKARI NEP Wide Field, and the a little bit dark gray region is the NEP Deep Field. So having AKARI data is not enough. Recently, Subaru HSC observation with GRIZ and wideband were carried out to cover the entire field of the AKARI NEP field. So this is very powerful because this allowed us to extend AKARI sources with photometric redshift to the full coverage of the NEP wide field. So besides AKARI and HSC, we also have other bands in our catalog. So in our band, we have in this multi-wavelength catalog that we present, this includes 42 photometric bands in total. which is very powerful. So with this powerful catalog, we are able to do SED fitting more precisely. So 36 bands are used from the multi-wavelength catalog, which I list here. So including Subaru and Midnight, Flamingos, and so on. Also, we have this most important AKARI IRC data, and all the sources must have, because of the SED fitting technique we use, we require the Herschel pass or spire detection to make the SED fitting better. And the technique we use is CIGALE. CIGALE is a SED fitting code, and this is a physically motivated modeling based on the energy balance principle. Therefore, with this technique, we are able to derive more physical properties of a galaxy, such as AGN luminosity, star formation rate, and so on. So let me show you the example. Let me show you the example of the CIGALE SED fitting. So this is the typical SED of the AGN. Let's focus on the green line. The green line is the emission from AGN. So for this SED of the AGN, we can clearly see there is a green line. That means there is emission from AGNs. But for this star-forming galaxies, there is no such a line, which means there is no AGN emission in this source. So this is how we distinguish whether this is AGN or star-forming galaxies. So let me show you our results. So in this work, we define source with AGN contribution larger than 20% as AGNs, which we call SED AGNs. And in total, there are 126 SED AGNs found in this work. And we also compare our selected AGNs with AGNs selected by traditional color diagram. So we found that we can recover 11 AGNs missed by previous work. This is because we have more bands. Therefore, our classification will not only be dependent on these two colors. We will have a more complicated agent selection. Therefore, we are able to recover these missed AGNs. And this is the result of our sample. So in this figure, we can see that when the total infrared luminosity is higher, the redshift is also higher. Also, the AGN contribution is higher here. And we really want to know whether AGN contribution depends more on total infrared luminosity or redshift. Therefore, we fix the redshift and total infrared luminosity individually and see the relation between AGN contribution and these two properties. So if we fix the redshift first, and we see that there is actually no clear relation between AGN contribution and total infrared luminosity. However, when we fix the total infrared luminosity, we can see that when the redshift is higher, the AGN contribution of the source is also higher. So we think that we propose that AGN contribution depends more on redshift than total infrared luminosity. So, and another thing is that we found two hylargs with very high star formation rate. For this, this is one example. For this source, the redshift is around 3.36, and the star formation rate is 10 to the fourth. fraction, agent contribution is 0.25. So we actually checked the SED of this source, and we found that there is a strong agent contribution. Also, we checked the optical and near-infrared source. This is their images, and this is the spectra of this source. So we actually found that this is the quasar, which is spectroscopically confirmed. So yeah, this is the extra finding in this work. So this is the conclusion. AKARI IRC is very unique. Its continuous 9-band coverage in the infrared enables us to search for dust-obscured AGNs, which is more efficient than Wise and Splitter. Also, we define the AGN sources with agent contribution larger than 0.2 in this work. With this definition, we found 126 AGNs, and we recovered 41 agents missed by Wise color diagram, and we, based on this SED fitting result performed with CIGALE, we found that agent contribution depends more on redshift than total infrared luminosity. And we expect future large infrared surveys such as JWST can help us reveal this relation. So this is my talk. Thank you very much.